The photosynthetic apparatus today. I've got a couple different sub-missions, but one of my missions basically is to bring to your attention another problem where there are probably non-trivial quantum effects, or I hope to make the case that there may be some non-trivial quantum effects, and they may also influence biology in line with the goals of the conference. So the systems I'm going to be talking to you about are resonant fluorogenic dyes. So these are dyes which, when they are free in solution, have a very low quantum yield, 10 to the minus 5, give or take. When they are specifically bound to biomolecular environments, the fluorescence quantum yield increases a lot, up to between 0.1 and 1. So you're talking about 5 orders of magnitude of dynamic range in the fluorescence, which is quite a lot. This is seen with a couple different dyes that have a similar motif. Right, a similar electronic structure motif. And I show two of them here. The one on the left is the chromophore of the green fluorescent protein, that's GFP here. If you're wondering why the Incredible Hulk was on the title slide, it's because apparently Bruce Banner expresses this guy when he's angry. And over here is malachite green. Malachite green is a dye that's been known for a long time. It's industrially reasonably important. Apparently you can use it to disinfect aquariums. But if you train an RNA aptamer against it and it binds to the RNA aptamer, then the quantum yield goes from about 10 to the minus 5 to about 0.2. If you do this with an antibody that's trained against malachite green, it goes up to about 0.6. The GFP fluorescence yield is 0.8. So again, we've got a big dynamic range. The motif that they have in common, which I'm going to suggest to you underlies the common fluorescence enhancement mechanism, is the fact that both of these dyes are resonant dyes. One of them is obviously symmetric from right to left here. This one is not, but in either case there are two low-lying Lewis structures that you can draw, and the two low-lying Lewis structures have two differences. They relocate a charge and they flip all the bonds. As far as biological function goes, here we have many body states. This arrow would be interpreted as a superposition normally, superpositions of many body states. Most people say that's non-trivial, that I've spoken with. I'm never clear about what's trivial. But over here, let's see. And in terms of biological function, this is man-made. This thing, however, was made by nature. Fluorescent proteins are known to occur all throughout the kingdom Animalia. They've been recently found in Chordata. That's our subphylum. No, that's our phylum. Insects, too, they're originally found in jellyfish. It's not really clear what their function is, but most of the functions have to do with the luminescence. So if you're going to talk about increases in quantum yield, you're talking about biological function. If it is quantum mechanical, then that is quantum mechanics. It's important to biology. Okay, so I've said that these dyes have two Lewis bond structures that you can draw. It is commonly held, and I'm not going to argue with this, that they do not fluoresce in solution because they undergo a competing mechanism. This mechanism, this reaction, is double bond photoisomerization. David Jonas mentioned that earlier as the reaction which is responsible for the perception of photons in us and many other animals. What happens is that a double bond flips its stereochemistry, but if there are two double bonds and they are delocalized, which one twists? As it turns out, in a Born-Oppenheimer picture you would get from normal quantum chemistry, in a resonant dye, for example, the anionic form of GFP, there are two pathways that are open in the excited state. And so you could potentially decay by both pathways. If you shut off the resonance, and GFP chromophore is interesting in this case because there are a couple different ways you can shut off the resonance, by protonating either at this site, or alternatively at this site. If you just pick one, let's say over here, add a proton, you've stabilized this structure over this structure by quite a lot. Now you're non-resonant, you have a definite double bonding structure, and you only twist about one bond in the excited state. So, this mechanism is apparently turned off when these molecules bind to proteins. If you look into the literature, the discussion is often dominated by the suggestion that the protein is sitting here holding the ring by a mechanical constraint mechanism. So that essentially the protein is more viscous, the argument goes, and so this ring, which is apparently bulky, cannot twist. There are a couple reasons to think that things are more complicated than that. Number one, if you make a mutant with non-natural amino acid mutagenesis of this guy, then it's non-fluorescent. Two, if you protonate this, and you would think if you have two pathways open, the environment has more work to do because there are more constraints it needs to satisfy. You would think that actually this situation would be less fluorescent than this situation. That's actually also not true. In addition, if you examine the electronic structure when the molecule twists, you see something that is reasonably interesting, and the environment would probably also notice. Namely, if you twist one bond or the other, you separate charge in the ground and the excited state in ways that are opposing the ground and the excited state, and which also depend upon the bond that twists. So, for this resonant case, there are two pathways. If you twist down one pathway, up here at the top bar, I've shown the electron difference densities between the ground and the excited state. You can see that the charge transfer upon excitation in this twisted region, which is dark actually, so you couldn't really go from S0 to S1 with a photon, and that's a problem for detecting the states. But the polarity of the charge transfer here is different from over here. For this molecule, where you shut off the resonance, you only have one direction of charge transfer. So, and as David also mentioned, so once you twist, you develop charge transfer character, and you would expect decoherence to happen then because the environment can detect the electronic field, or the electric field. Once these things are twisted, they usually decay to the ground state by conical intersections. You can examine these with quantum chemistry techniques if you would like. The dynamics around these regions should be very non-trivial. And these are points basically where the electronic and nuclear modes become entangled. So, if you examine, again, the charge distribution around the conical intersection in a special plane, which David mentioned, which is called a branching plane, and I'll just leave his explanation there for the moment. There's a special two dimensions associated with the conical intersection scene. If you plot the Mulliken charge, which is just one way of assigning charges to atoms in a molecule, you find that on the ground in the excited state, it changes very abruptly as you traverse the branching plane, and this is opposing the ground in the excited states, like the charge transfer states that are accessed when the molecule twists. So we have twist-dependent charge localization, and we have conical intersections which separate diabatic states with opposing charge character. This latter point is interesting because this means that the environment can move the intersection around, and I can show you some evidence for this as well. All the plots here were generated with multiple spawning dynamics. Multiple spawning dynamics was an invention of Todd Martinez, my old friend. Basically what happens here is that the molecule is twisting. These are multiple spawning dynamics that were done with an ab initio wave function. Over here, there's a semi-empirical reparameterized wave function. There are a couple things I want you to notice. First of all, this plot over here, all these red traces were dynamics of a molecule in isolation. The black trace here is what happens when you try to model the environment by putting this dye in 50 water molecules. So this, and the idea behind this very quick speed up of the decay is that the intersection itself is being moved, stabilized. I also want you to notice over here that these dynamics, which are all for the molecule in isolation, you do have different bonds twisting. So up here is the neutral form of this molecule, which has one, for which you should expect to see one bond, I have said, twist. Down here for the resonant case, you actually are also seeing one bond twist. What this means actually is that the dynamics that you get can be very sensitive to the potential surface near the Frank-Condon point. Now, in order to talk about what happens when this thing twists, and what I'm basically going to do is suggest to you that there's a particular form of the electronic structure, a minimal model that we've come up with that reproduces this physics, or the physics I've just told you about. If you want to interpret one of these resonant symbols the way it is normally done, this is a superposition of many body states. For example, if you want to take one particular perspective, you might say that each of these Lewis structures, or each of these bonds, represents a bonding function, which would be a function on the Hilbert space of two sites, each site being a pi type orbital on an atom. And you could make an approximate state by perhaps making a product of these different bond functions and then anti-symmetrize the whole thing. One thing I want to point out about doing this is that if you're using a common set of localized orthogonal orbitals on the atoms, then each of these bonding functions has a specific form. We're going to call one of these a perfect pair. And the form that it has is that you would have a contribution from the covalent function, which is the singlet function that we've seen earlier, and also a contribution from a whole pair state. This is very important for the bonding, and in an orthogonal valence bond basis, this gives you the bonding. So the bonding that is a result of the overlap in non-orthogonal pictures becomes due to the contribution of the whole pair states in an orthogonal model. It's actually going to be important again in a moment. So dyes like this have actually been known for a long time, and they were some of the first dyes to be generated with synthetic organic chemistry. And so they have a long history and are partly responsible for the growth of the chemical industry. In particular, it's known, there was a large body of work done around this time by this guy and others that discovered certain color patterns or certain patterns in the absorption of these dyes. One of which I'll just mention as an example, is that a dye that is asymmetric is never any redder than the mean wavelength of the parent dyes. This deviation is called the Brooker deviation. Brooker stated that this deviation is a measure of the difference in basicities of these two rings in any given dye. He showed that scales that you can obtain by taking different reference rings and making dyes out of them, paired with different rings, roughly agree. And you can show that this deviation is correlated with the Hammett scale of basicities. What this basically is saying is that we should have one site per ring, because the basicity is normally interpreted as a one electron energy. And there's a lot of literature that goes into this Hammett constant in particular, showing that it can be correlated with molecular orbital characteristics. So this is an interesting statement because the basicity scale was originally defined in terms of the excitations of the entire pi system of the dye. But this empirical result from the middle of the last century suggests actually that we can think about this in a reduced way. There's also been some theoretical work that dates back quite a long time. For example, one result that I want to familiarize you with, because I'm going to show you in a minute that it emerges from a quantum chemistry solution, is a two-state Hamiltonian that was originally devised by Platt to reproduce Brooker's data. Platt's Hamiltonian looks like this. This E with the tilde is the harmonic mean of the optical gaps of two symmetric dyes, and delta ELR here is the optical gap of an asymmetric dye. These are symmetric parents, it's the asymmetric dye. He defined a Brooker basicity as such, and then by construction, if you diagonalize this matrix, you get back the energy gap of the original asymmetric dye. Platt hypothesized that these basicity differences, if they can be written as differences of basicities, each of which correspond to the rings and not the dye, they should obey these consistency conditions. Platt showed that they did for Brooker's data. This suggests, as I've said, that actually, if you want to create a minimal model of this system that reproduces the physics that I've described, the charge localization, this twist dependent, and the conical intersections, you might be able to do it with this. Because there are many dyes that have similar behavior, we expect also that there's this model reduction that can be accomplished. That would suggest an ansatz like this, or an electronic Hilbert space that looks like this, from which you could generate these singlet configurations. There's 6 singlet configurations for 3 orbitals. Here the excess charge is a negative charge, but with a little bit of thought you can convince yourself that if it's a positive charge, you would also get a 6-dimensional many-body space. I'm going to show you now that the color theory that I mentioned comes about from a solution of a particular quantum chemistry problem. This is the quantum chemistry problem. And I won't say much about it, although I have a lot on this slide. What I basically want to point out is that it's a frontier orbital model, so that if you take a particular reference state, take a window of orbitals around the HOMO-LUMO gap, or the Fermi level if you like, and rearrange the electrons in that window amongst all the orbitals in that window, then you generate a set of configurations. You can solve the configuration interaction problem in this many-body basis. doing exact diagonalization if you prefer that terminology. And then you get energies for the states. You can then optimize the orbitals according to a state average, and you have state average gas SCF. You can parameterize individual energy like this. And here's the state average. Usually these weights would be set evenly. I like gas SCF because this expression here, and the fact that the one electron orbitals and the many electron orbitals both span Lie algebras means that you can use something that Levine and Tishby said a long time ago and interpret this state statistically if you want. So, if you solve the gas SCF problem for dyes like this, and it doesn't really matter which dye you choose. It appears to be very transferable. Then you come up with a solution that looks like this, which is exactly what I have described to you, based upon the argument that the site should have one electron state associated with it, or the ring should have one electron state associated with it. This appears to be extremely general. Here's malachite green, here's oxazole yellow. Oxazole yellow is the dye that becomes fluorescent when it binds to DNA. I've investigated this for several dyes, and you always appear to be able to find the solution if you look for it. This solution is the color theory that was described by Platt and Brooker in the middle of the last century. In particular, the fact that the orbitals are approximately transferable. Here again, I've taken states or rings from the GFP chromophore, protonated them at different sites to create different rings, made a complete set of all the dyes that could be thus generated, done the electronic structure, and as you can see, these orbitals don't change their shape much as you go across a row. This is exactly the pattern that you would predict based on the transferability of the Brooker basicities. If you fit all the excitation energies that you calculate using this active space, and then with perturbation theory applied to it, multi-state, multi-reference perturbation theory at second order, you take those excitation energies and you extract, using Platt's consistency relations, basicities for each of the rings. You find that actually the entire excitation set can be fit with this two-parameter model to within an error that is much less than the expected error of the CASB-T2 calculations themselves. So in fact, the excitations fit a Platt-type model exactly. Furthermore, because you have localized orbitals, you have energies associated with the orbitals, and if you'd like, you can extract one-body basicities and compare them to the many-body basicities. Again, you get a good correlation. All of these dots here are basicities that were extracted for specific dyes in this entire set. So, but they all fit the line fairly well. So, I guess what I've shown you now is that there is a solution that not only justifies, there's a numerical quantum chemistry solution to the electronic structure that not only, I'm going to tell you that it reproduces the essential physics that I've already described, but it's also consistent with 100 years of experimental data, which you would want. If you look into the color theory, again way back when, you find that there's a third state predicted by the theory, in particular the one electron transfer element that would move a charge from one end of the dye to the other, should not be big enough to explain the optical excitation. And so the way that the theory was put forward at the time to get around this problem, again, middle of the last century, was to postulate a higher lying state with charge on the bridge. This state interacts with the even combination of these two extreme structures, but not the odd combination due to symmetry. And so this forces down the even combination as opposed to the odd combination. This is enough to give you an optical excitation. Of course, if this interaction is unitary and you start with 3 states, you should get 3 states out at the end. So the prediction is also that there should be a higher lying state in many of these dyes, which may not be very bright, but it should have orthogonal polarization. In fact, for dyes like malachite green, you can see it in a linear spectrum. For dyes like Mickler's hydro blue here, it's quite broad, but it can be detected. It turns out actually that this state becomes very important to describe the photoisomerization process. Because in order to actually describe the diradical becoming localized on either bond, you need this state here in order to mix with these two states. And this also explains the charge localization. So over here, what I'm showing you is that this solution I've described that happens to explain the color theory of dyes from way back then has a structure that doesn't change as you twist either of the bonds in the molecule. So we have a diabatic basis that is approximately continuous or smooth over the relevant potential energy surface. You can take the solution that you obtain in the six-dimensional many-body space and block diagonalize it down to 3 dimensions. This also works over the entire potential energy surface, or at least both of these twisting coordinates. And you find that actually the states that emerge have a valence bond character. I told you earlier that you need ionic states in order to get bonding in a valence bond picture with orthogonal orbitals. I told you that for a reason. It was to show you that basically when you do this block diagonalization, you get ionic contributions exactly where you would expect them based upon these arguments, using the simple many-body basis that I showed you before. If you twist one of the bonds, then you single out one structure which still has this bonding contribution. If you twist the other bond, you single out another one. What's happening is that when you twist one bond, you take this resonance and you collapse it, and you send one of these structures to the ground state. It is the state that has a single bond on the twisted bond, because otherwise it would cost energy. And the other 2 states here are now the even and odd superpositions of the remaining states that you have out of the 3. This explains the charge localization that is twist dependent and dependent upon which state you're in. So, we've taken this, what I want to show you is that you can use this solution and you can actually plug it into an analytical model and you can get the right physics. So, taking this, continuing with this perspective that you should have a reduced model to describe the general physics. If you actually take a 3-state Hamiltonian, which for simplicity let's assume to be degenerate on the diagonal, and you parameterize the couplings according to overlap arguments, which are a traditional approximation for valence bond type methods, you would come up with this model Hamiltonian. It's 3 by 3. We know the analytical solution, so we can study what happens. And basically you get most of the physics that I described in the very beginning. In particular, this can describe 2 pathways. It can describe twist-dependent charge localization. Here I've just used an RGB color map to show you where the density is going. And it also describes twisted conical intersections. Interestingly enough, it also describes planar conical intersections with this 3rd state that I mentioned. And what it, again, this model is diagonally degenerate, but what it suggests is that actually if you have biasing in the first excited state, then you may be able to access the 2nd pathway by preparing the higher excited state and having it descend then through the intersection, but prepared now in a different part of the S1 surface that favors twisting about a different bond. Another interesting thing that this predicts is that also the conical intersections are joined, so the intersections about each bond in one of these dyes should be part of the same seam. And that's all I have to say right now. We're working on fleshing out that model. I'd like to thank the organizers for inviting me to speak, and also all these funding organizations. 3S should probably be up here, I suppose. I apologize for that. But, and all the people with whom I've done the work. And you for your attention. Thank you.
Thank you. So, questions?
When you have sort of a longer chain plan, then you have to put in basically one of these states for each double bond going down to connecting?
Not sure about that actually. I think in principle yes, but you may be able to get away with a more reduced description. This seems like a problem that could be treated with an intermediate Hamiltonian, the sort that John Paul Mallory has suggested. But it's also true that the dyes that are used for fluorogenetic labeling are usually not that long.
Mm-hmm.
I think 3 methane units is about the longest one that's usually used. Most of them are monomethane dyes. And in fact, it's an interesting point to make that as you get longer, the quantum yield in solution actually goes up too. I'm not entirely sure why that is yet, but about that as well.
Models that you construct, I think this is not a Hamiltonian you could run dynamics with, right? This is essentially a potential energy surface to illustrate some process, some photodynamics. But I mean, if you have a conical intersection of tuning modes, they are important for the dynamics, which are left out here, obviously. But this is essentially for illustration purposes.
This is for illustration purposes, yeah.
Okay.
Yeah, that is true. You would need, well, there are two conical intersection seams. To describe that, you would need a 5-dimensional branching space, I think. 3-state intersection, I believe, has 5 dimensions in the branching, no longer plane, but subject to plane.
More questions?
So if you're telling us about entanglement between the vibrations and the electrons,
Yeah.
does that have any consequence for the green clothing operation?
I believe it does, actually. In fact, I recently, well, myself and my coworkers have recently proposed that this is exactly the mechanism for reversible photo switching in some of these proteins. You can turn some of them on and off. And it's interesting to note that the absorption of these guys is redder than most. This suggests by Brooker's rule that perhaps the chromophore is resonant. But the suggestion that we've made is basically that the decay around the conical intersection is tied to proton modes. And so this is a mechanism for coupling proton transfer with the photoisomerization. That's exactly what you see in those proteins that can be photoswitched.
Seems that everybody's waiting for coffee. I hope coffee is ready already. In any case, let's thank the speaker again.